Hello class, today we're going to go ahead and talk about integration rules. So today we're going to learn about the definition of an integral using Riemann sums. Alright, so what we need to know is that we have been integrating, and the symbol of the integral looks like an integral from a to b given a function with respect to x. What we're going to go ahead and learn today is the following, that this is the area under the curve, and we can find it by using tiny rectangles, whether it is the left or the right under the curve. So all we need to do is notice that we can find the limit as n, the amount of rectangles goes to infinity. So we want to get the amount of rectangles under the curve to be as many as possible. And we're going to add those rectangles, so we're going to go ahead and sum them when we start with one rectangle all the way to our last rectangle, which should be infinity. Now, that being said, we know how to find the area of a rectangle. It's the length times, the height times the width. So it's going to be our function. Let's go ahead and say f of xi being our first rectangle times the width of the rectangle, which we know is delta x. This will be the same as finding the integral. And if we go ahead and do this, it will be a very exact, it will actually be the exact area under the curve. So let's go ahead and do a first example. So it's going to be the integral from 0 to 4, given that the function is going to be x cubed with respect to x. Now, what I encourage you to do is that you have to go ahead and write this so it can help you out. So we're going to go ahead and write that same equation, and we're going to find out all the little parts. So I strongly recommend that you write this on your own. So let me go ahead and make this a little bigger. So it's going to be the integral is denoted from a to b for the given function dx when we are given the limit as n goes to infinities, with the amount of rectangles being infinity, starting at 1 to infinity, and we get the area of the rectangle because of its height times its width. Okay, so let's go ahead and find each individual part. So let's go ahead and find our delta x. Well, we learned in our notes that our delta x is the equation b over a divided by the n, when n is the given rectangles that you want. So let's go ahead and do that in red. Remember, our a is our bottom term, so it's going to be this right here. It's going to be b is our top term, so it's going to be 4 minus my a, which is 0, divided by n. That will give me 4 over n, which is my delta x. So I got this part already, so let me go ahead and highlight it so I won't lose it. The next part that I want to go ahead and find is my height of each individual rectangle. So that is given to me as the equation x of I is given to me as a plus x I, our change in x times the term that we're doing first. So it's I being 1, I being 2, and the amount of rectangles, and so on. So this goes pretty much the same. My first term is given to me as my lower bound, so this a, which in this case is 0. So 0 plus my change in x, which I have just found right here, and I said it was 4 over n, times my term right here, that is the I term, so times I. So to make this a little nicer, we got x of I is given to me as 4 times I over n. Now all you have to do is find out, well, what is this equation that I'm going to use? Well, look right here, I got x to the third, so my function is most likely going to be x to the third. Now, very important, this part right here in green, this part right here replaces the x's, so everything here. So let's write our answer. So our answer should be the following. If we go ahead and mimic this part right here, our answer is the following. The limit as the rectangles go to infinity and we add their areas from I being the first rectangle to the last rectangle, which is infinity, we get the following. The function was something cubed, and my new x's are given to me here. This right here will be my new x's. So it's going to be 4i over n times my delta x, which I can see was given to me here as 4 over n. This right here would be our answer. This summation notation as n goes to infinity is the exact integral of the area under the curve. Thank you. Bye.